Okay, so the first type of flip-flop we've seen is a Theta flip-flop. So we're going to go for a behavioral description approach, where we're not now going to look inside what logical or circuit we have inside this block. So as this symbol is showing, we have a D line. So this is one of the inputs, and then a clock line CK. We have a small triangle here to typically show that this is a clock pin. We have preset and clear lines. These two lines, the preset and clear, typically is used to set the state of your data flip-flop, typically initially, but it could be used, of course, during the process. We're going to see that with counters. If you need to set at any point in time, you need to set the state of Q and Q bar, you can use these lines. Yeah, it's preset and clear. Now, the way the data flip-flop works is very simple. So at every rising edge of your clock, you can see here this clock line is not active low because you don't have a small circle here. So for every rising edge on clock, whatever state you have on D is transferred to Q. So Q is equal to D for every rising edge. We've seen that. Yep. So this is how. So you can read that in your notes. But this timing diagram shows that very well. So for every rising edge in the clock, so whatever is on D is transferred to Q. Yeah, as you can see here. So important here, for example, you see that segment here. So your D has changed state, but your Q doesn't change state because it can only do that in synchrony to your clock. So only at the rising edges do you do the circuit check for the state of D and transfer that to Q. So that's an important point. Now, second type of flip-flop, we see the T-type flip-flop. So this is a block diagram very similar to the T-type, except that now with T line. So toggle, T stands for toggling, and toggling means change state between high and low. So again, the operation of a Theta flip-flop is very simple. We're taking again a behavioral description approach here, where we're just describing how the circuit works without going inside what the block diagram. You can also, of course, if you're interested, you can read more on that, how actually this is done using logical gates and other kind of electronic circuits. So if you're interested, you can read further. But for this module, we're not going to that depth, like we say. Okay, so how the circuit works, again, if your T there is low, so your Q doesn't do anything, it just maintains a state. But if your T is held to a high logical state of 1, so for every rising edge on your clock, the Q will toggle. Q will not take a state of T. This is what the D does. But in the T-type flip-flop, so for every rising edge on the clock, if your T was high, Q would change state. So if it was low, it becomes high. If it is high, it becomes low. Yeah, so this is the behavior description for Theta flip-flop. So this is shown in this timing diagram here. So for every rising edge, if T is low, then Q would maintain the same state. But if T is now high, whenever you have a rising edge, Q would toggle state. Yeah, so you can see here's toggling state. But for this rising edge, since T has been made low now, it would maintain the same state. So that's how the Theta flip-flop can be described. Now, the JK flip-flop is nothing new here. It is a simple method for us to implement the T-type and D-type flip-flops in the same flip-flop. So if you have a JK flip-flop, you can use the J and K pins to actually make this flip-flop become either D-type or T-type. And this is summarized. Again, your preset and clear lines here are just used to either set the state of Q or clear the state of Q. And since now it's active low, it means when PRE is made low, then Q becomes high. So similarly, if CLR line is made low, then the Q becomes 0. You won't have a situation where both PRE and CLR are made low, because this is an indeterminate state. You don't know what will happen. So you have to avoid that. Now, once you have set the state, then using J and K there, you can decide what behavior you want from this flip-flop. So this is summarized here in this part of the truth table. So if your J and K, as you can see here, if your J and K are different states, yep. So if J is high, K is low, or if J is low and K is high, it behaves like a D-type flip-flop. And you can see here the state that the output takes the same state as J. So if it is high here, it is high. If it is low, it is low. Means if it is behaving like a D-type flip-flop, in that case, your J is representing your D line. Remember how the D-type flip-flop works? Whatever at every rising edge of your clock, the state of D is transferred to the output. So the question crops up now: if you have the J and K, which of these two is actually the D? Because we need to have the D to know which of J and K is transferred to output. So as you can see, what is transferred to the output is actually J. So if it is high here, you can see your output is high. If it is low, then output is low. So it means when you make J and K become different states, it behaves like a D-type flip-flop, that's fine. But in that scenario, your D line, which you need in a D-type flip-flop, is nothing but J. Yeah, because it's edge here, it is edge, and L and L here. That's an important point to remember. If you make your J and K both low, then this is not doing anything. It's like the flip-flop is off. If you make your J and K high, it is behaving like a theta flip-flop, so it's just going to toggle state, like we said. Okay, so again, the JK flip-flop is like a universal flip-flop. If you want, you can use it to achieve both the T-type and D-type. Okay, now some applications of flip-flop. So let's look at the storage register. So what a storage register is, basically it would, how a storage register is constructed. First thing is constructed from data flip-flops. So in this case, we have 4 data flip-flops connected as shown here. Yep, so you can have more. So if you have 4 data flip-flops, it means you can deal with 4 bits. If you wanted to deal with 8 bits, you would need to have 8 data flip-flops. Let's see what this is doing. You can see here you have an enable pin here connected. So it's common for all of them. You have an enable, means this is going to enable all this data flip-flop to work. So you need to send a low here. If you send a low here on this enable pin, it's going to enable your flip-flop and to start operating. Yep, so it's just a line. Now, once you've enabled it, now we know how the data flip-flop works. It's going to take a clock, and for every rising edge on the clock, it's going to take the whatever state is on the D line is going to put on the output. Okay, so you can see here the clock is connected to all the data flip-flops. Yep, so all the data flip-flops share the same clock. It means whenever you have a rising edge on the clock, it's going to transfer the D to the respective outputs at the same time. So all these flip-flops are in parallel in a way. Okay. Okay. So where can we use such a circuit? Why we call it a storage register? Let's understand what's happening. So this B node, B1, B2, and B3, they are input bits. Yep. So B node, B1, B2, B3 could be coming from some process. So you have a process where you have a state to monitor. Yep. So this B node, B1, B2, B3 could be a voltage, could be anything. Let's say a valve is open or a door is closed. It could be anything. So a light is on or temperature sensor is above a given value and so on. So at the rising edges now of your clock, you're taking the state of your system and transferring on your output. And for one clock cycle, so let me just draw that. What I mean by one clock cycle. So let's just try to draw a clock here. So let's say this is the waveform you will have on your CK on your clock. Yep. So it's just like this. Okay. So since the data flip-flop works on rising edges, so this is one rising edge, and then the next one is here, and the next one is here. Okay. Now we know that at every rising edge, this is at this point that your state on your D line is transferred to output. So let's say at this point here, you've transferred B node onto Q node, B1 onto Q1, B2 onto Q2, B3 onto Q3. That's fine. So for one whole clock cycle, so from this one to this one, it depends on the frequency of a clock. So from all over this whole time here, your B node can change state, but your Q node will not change state. So it's going to store the state that you had on B node. So B node could be a signal which is fluctuating based on the process, but whatever state you had at the rising edge of your clock will be maintained at the output for at least one clock. This is very important if you have a process and you want to have a stable output at on a given line to be able to read it by a microcontroller or any process controller. The signal should be stable for some time at least. So this storage register is allowing the state that you have at a given input to remain stable for at least one clock cycle. This is why it's called this is why it's called a storage register. Yep. So maybe the name is now making sense. This circuit allows you to store the state of a bit onto a given line, in this case Q node, for a certain amount of time, so that you have time to react to it, to store it in your circuit, to read it, and so on. So this is what a storage register is about. Yeah. So very important circuit. Like I mentioned, this one is a 4-bit storage register because you can deal with 4 bits here. If you wanted to have 8, you would just simply increase that Okay, you will simply increase that and add more data flip-flops. So you have a question through a sheet where you're asked to design, I think, 6-bit or 8-bit storage register. Nothing difficult there, just going to add more of this. So there's a comment here. You can find the clock is applied to all 4 flip-flops. We've seen that. So same clock is applied to all of them because you want this transfer of input to output at the same time. So everything is synchronized to your clock. Now the enable pin should be driven low for the flip-flop to operate. So anytime when you want this transfer to occur, you would of course send a low signal to this enable pin there. So your data flip-flop works, and then when the clock comes in, it transfers to output. So you have an enable pin in this one. And as you can see, you have a small node here. It means it's active node. So in this circuit here, you have an enable pin, which you need to drive low for the flip-flop to work. If you make it become high, the flip-flop would not work. So it's just like a control line. Okay, so very simple application of a data flip-flop storage register. Again, just more recap, it allows you to store the state of an input at an output on a line like Q0, Q1, and Q2, Q3 for a given amount of time, so that you can work on it, you can read it, or you can store it anywhere you want. That's important. So it is storing the state of your inputs. Remember, B node, B1, B2 could be fluctuating over time. Let me just try to draw that. So let's say B node B1 is doing something like this, is fluctuating on a line. You have some fluctuations. At some specific time, you read it here. So you are able to store a state there for some time. Yep, store it for some time at least. So you have a stable state on your output. Even now, in the next moment, it starts to fluctuate a bit due to interference and so on in your system. So you are able to store that state there for some time for you to react to it. If you do not have the storage aspect in your electronic circuit, it becomes difficult for you to actually take that output because it's always changing. Yeah, that's an important property of circuit. So reality, if I want to say any control system you're designing, you would need to have stable states on your lines. If something is always changing, fluctuating because of interferences, it becomes difficult to act on these things. Now, second application we look at is called shift register. So again, a shift register is going to be implemented using data flip-flops. Now, why shift register again? So let's try to look at that. So I'm just going to skip down here just to show you this timing diagram here. What is this one showing? So you can see there's some crosses here. So this crosses means that in this state there, you're not interested with the state of your signal. Then at some point, you start having a high and a high, and then a low, and then a high, and so on. And then at some point, it again becomes not interesting for you. Now, can you see all the states you find there? One is synchronized to a clock. So this one you have here is high for a given amount of time, but it's important to know that it is only at the rising edges that you are interested. So you have to be able to maintain this high for at least a certain amount of time corresponding to the rising edge. So if you wanted to read this signal properly without interference, you would need to ensure that the signal you're reading is high for a certain amount of time, so that it is corresponding to a rising edge. Same comment for this one there. It should be synchronized to this clock. So when this rising edge is coming, you have to make sure that this is not in transition. This is called a transition there. Now, why you can ask me the question, why this line here is not a straight? That means it's not vertical, it is slanted. Because in practice, when you want to change any state from high to low, it cannot change abruptly. For a clock, it is, of course, you have special circuits to do that. You have crystal circuits to change very fast. But typically, when you have normal circuits which are operating, it's not easy to change from high to low very quickly. Now, we know that to change from high to low, you need a certain amount of time, but you have to ensure when you're making this change on a line, it is coming to the required state at the next rising edge. So in this case here, if you wanted to set a 0, you want to make sure that you have changed from 1 to 0, so that when the next rising edge is coming, you are at a 0, because this is where it's going to be read. Now, what you see here in this these two signals, so it's a clock signal, like we've seen. A clock signal is going to be sort of a signal that the whole electronic circuit is going to be tuned to, it's going to be synchronized to it. Whereas this one is a data you want to transmit. So this data is shown in this format because it's serial data. So whatever is sending on a line would be high for some amount of time. If you wanted to send a 1, it's going to be maintained high, and then this is going to be transmitted along an optic cable or a normal cable. And then if you wanted to transmit after this one, another one, means a high, you would maintain the line, but make sure that this is corresponding to your rising edge. If you wanted to transmit a 0 now, because the next bit you want to transmit is a 0, so you're going to now change the state and make sure that at the next rising edge, this is transmitted. So basically, when you send this signal on the line, you would also send the clock signal along with it, so that what the receiver, you are able now to read back. You want to construct back this bit. In this case, it's 1011, so 1011. If you're sending that on the line, you want to be able to read it back when you receive it at the receiver side. If you imagine, for example, the NBC is sending some, let's say, some video signals on a few digital technology, and you're sending that through from a transmitter which you have at the NBC, and then you have the receiver through your antenna at home, or the receiver is going through optic fiber, and then you're receiving it through your router, for your Wi-Fi or Mighty box at home. So this signal should be reconstructed back. So it is sent here in that format, and then you need to be able to receive it back. So it is done through this type of circuit there, a shift register. So let's see how it works. So it is composed here of Theta flip-flops, and you can see the clock is connected to each one of them individually. So the same clock is connected to all the Theta flip-flops. And then this signal which you find here is connected to only the first Theta flip-flop. That's very important. So it's not connected to each one of them. It's connected to the first Theta flip-flop only. So when the first one is going to come, when the first signal comes, which is a 1, so 1 comes there, and then at the rising edge of the clock, this 1 would be transferred, because you know how the Theta flip-flop works. It's going to be transferred onto the node. So this is what happens initially when the first one comes. Fine. Now the next bit is coming, which is a 0. It has its clock. So can you see now the output of this flip-flop is connected to the input of the next one. So at the next rising edge on the clock line, what would happen now? When this 0 is transferred from here to here, the 1 which was here will be transferred next here. Same thing when this one comes in now, it has its rising edge. So this rising edge will make this one come on this line on the node, but what was on the node would go onto D1, and what was on D1 would come here. And when the final one comes in, this one will be on this line here, is going to be transferred to at this rising edge onto the node. So D node is going to take a state, this 1 here. Then D1 would of course take a state 1. Then D2 would take a state 0, and D3 would take a state 1. So what have you been able to do? What have you done actually? This signal was transmitted serially, means one after another. But by sending the clock along and using this circuit there, you are able to separate your bits into 4 individual bits, which is not now in series, but now is in parallel. These are 4 individual bits. So this data, which was sent serially on the line, has been separated into the individual bits. So it could be 1, 0, 1, 1, which is what you sent. So this was called a shift register. You are shifting the bits in turn. So ultimately, when all the bits have been transmitted, you have recovered your original data, and then you can act on it. So I hope it's clear how this is working. So if you want to have a 4-bit register, shift register, so you're going to use 4 Theta flip-flops connected in this fashion. If you want to have 8 bits, you will have 8 in connected like this in this fashion, so you can extend it. So I hope these 2 applications there are okay now. So the storage register and the shift register using Theta flip-flops. Okay, so you can read more on that. There are lots of more information given in your handouts. So you can read on that and try to attempt the question tutorial sheet. If there's any issue, we can come back to that in detail. Now, next one we've looked at is the Theta flip-flop, which is used to create counters. So if you connect it in this fashion, so what's something is missing here, you need to have a triangle here and here for the clock. So if you connect a Theta flip-flops in this fashion, where in the first Theta flip-flop you have a clock which is connected, and then the next one is not, so this clock is not connected here, but the output Q of the first Theta flip-flop is connected to the clock of the next Theta flip-flop, and then you're maintaining your T line high everywhere, and then you're collecting Q1 and Q node in this fashion. So this is what happens. So if you assume your Q node and Q1 were initially low, you can do that using the clear pin. Because the Theta flip-flop has a clear pin that's shown here. So you can initially just set your all your outputs Q0 and Q1 to 0. And then when the next rising edge comes, if your T line was high, it's going to start toggling, as we know. So Q0 is directly connected to CL, so the clock. So for every rising edge on the CLK signal is going to toggle. So you can see here, for every rising edge towards low, it becomes high. Next rising edge becomes low, high, low, and so on. Now, since we connect the Q0, the output of the first flip-flop, the clock of next Theta flip-flop, now this Q1 here would not be sensitive to this clock, but to Q0 itself. So for every rising edge in Q0, is going to just toggle. Yep. So this is what you see now. So you can see the frequency is halving from here to here and from here to here. Now, what we do is we just collect the states Q1 to Q0. So we make Q1 the most significant bit, which is the flip-flop, which is on the right completely. So this one is the most significant bit of the number you're representing, and then progressively when you go to the left, they become the least significant bit. So you put Q1 first, which is the rightmost flip-flop, and then Q0. So if you collect the states there, see 0, 0, so you can see 0, 0, then 1, 1. You're taking 1, 1, so Q1 first, and then Q0. So 1, 1, 1, 0, 0, 1, 0, 0. So now, once you represented that in that table there, you can clearly see we are actually doing a down counter. So it's being 0, 3, 2, 1. So if you were to connect these bits there to 7-segment display, 7-segment display allows you to convert any binary number into equivalent decimal number. So you will be seeing on that 7-segment display 3, 2, 1, 0, 3, 2, 1, 0 will be displayed there. So when you go to the lab, you will have the opportunity to work with a 7-segment display. Now, instead of using just two flip-flops, if we now connect 3 in the same manner, so we have a clock signal, this first Theta flip-flop, all the T lines are held high, and successively the output of one flip-flop is connected to the input the clock of the next one, and similarly this output is connected to the clock of the next one. So if we do that and we follow a similar procedure, so now we have Q0, Q1, Q2. Bear in mind that Q2 now is the most significant bit. So the rightmost flip-flop is the most significant bit, and then this one is next, and then this one the least significant bit. So if you do that and you collect all the states and you make them into a binary number, then you're going to get that. So it's again a down counter now. So 7, 6. So if you connect these bits via the 7-segment display, you will see these numbers displayed. Now the frequency at which this is going to change, of course, depends on the frequency of your clock. Yep. So for every rising edge, you are having a change in state. Yeah. So when you go to the lab, this clock there will be simulated by you pressing a button. So it doesn't need to be as regular as seen there. The point is, whenever you have a change from low to high, so when you press the switch on your electronic board, it is then that the counting would be done. So it doesn't need to be a regular square wave like you see here. In your case, it depends when you're pressing this switch that you create the rising edge. That's important. But if you were to connect it to a, let's say you connect this to a clock of 1 Hertz. 1 Hertz is initially period of 1 second, so the number will be counting. So 8, 7, and so on. It's not 8, sorry, 7 rather, because it doesn't count 8 is 1. So 7, 6, 5. It's going to change state and do the counting for every 1 second. Yep. If you use a very high frequency, you won't even see the number changing. It's going to be too fast. Alternately, if you choose, for example, a frequency of port 5 or port 1, it means it's going to take more and more time to change, so you can see the numbers changing. Okay. Now, what we've done next here is, remember, these circuits were sensitive to rising edges. So what if you make the change in state sensitive to falling edges? So how can that be done? Simply by putting a circle there to say that this Theta flip-flop now becomes sensitive to falling edges, means low state of your clock. So if you do that, what do we see now? If you take the falling edges of your clock and then do the toggling, you find now you get an up counter. So if you again assume Q2 to be the most significant bit, so you get 0, 0, 0 and 0, 0, 1. So this is in a way that 0, 1, 2, 3, 4, 5, 6, 7, and then again 0. So you're doing now up counting. Yep. Okay. Now the next thing you want to look at is, what if you wanted to count not a 2 power n number, because till now we have seen that you can count, let's say, from 0 to 3 or 0 to 7, means it's something 2 power n minus 1. Yeah. But what if you want to count, for example, from 0 to 10? What happens? So this is what is shown here. If you want to do a modulo 10 counter, so if you leave a flip-flop on its own, yeah, it's going to count from 0. So if you use 4 flip-flops. If you use 4 flip-flops as shown here, it's going to count. So it's a modulo 16 counter because 2 power 4 is 16. So it means you have 16 states. It's going to count from 0 to 15 if it's an up counter, or 15 to 0 if it's a down counter. It depends what you're doing. Are you having a theta flip-flop which is sensitive to your rising edges? So it's going to be a down counter, or falling edges is going to be an up counter. We've just seen that moments earlier. So if you have 4 theta flip-flops, it's going to be 2 power 4. So it's in modulo 16 counters. So it's going to typically, if we consider up counter from 0 to 15. But what if you wanted it to count from 0 to 9 only? So 0 to 9 means you have 10 states in modulo 10 counter. Yeah. So basically in that table there, it means when you reach 9, you don't want to see 10. So this state there should actually bring back your counting to 0. Yeah. So if you want to represent that very easily, so it's going to be exactly like this. This circuit would be like this with one additional flip-flop. Let me just do that for you. Just do that in Paint and show you how it is done. Okay. 1 minute. I'm just going to shift Paint. Okay, so I brought that to Paint there, and I've shared the screen with you. So basically, what always, if we leave it in that state there, it's going to count. If say this is a modulo 8 counter, in that case, there is going to be a modulo 8 down counter. So if you want to make it become up counter, you will simply do that chain there. Just going to put a node in front of your clocks, yeah, like this, and then just taking it. Now it's okay. So you're just going to do something like this, and then put all the clocks to be active low. Okay, and then you would just, if you want to have now a modulo 10 counter, so modulo 10 counter means you will need to have at least 4 flip-flops, because if you have 3 flip-flops, it's going to stop at 7. So you're just going to have 1 more flip-flop. Yep, so you have this one, and as usual, you would just connect this line there to the previous clock, the previous output. Okay, so this is, and this one is going to be Q3. Okay, so if you did it in that state there, it's going to be an up counter and it's going to count from 0 to 15. Now, what if you wanted to stop? So you want to do a modulo, if you want to do a modulo 10 counter, up counter. Yeah, so if you want to do that, it means the binary state which represents 10, we know is 1010. So it means this is 1010. So when Q, I just do that. So when your Q3 is 1, okay, so this one here is for this one. So it should be 1 here, 0. Sorry. 1 and 0. So this is where what would be your 10. So when you reach the state there 1010, it means you want to just reset. So you want to go back to 000. So you would use this state there to reset your output. So what can you do here? You can simply use, and I'm just going to put it here. You can simply just have an AND gate. just trying to draw an AND gate for you. So you just haven't. So if you just choose an AND gate, okay. Now the output of your AND gate is going to be high when all the inputs are high. So if you want to connect this one, for example, to your AND gate, so basically you're connecting all the states there. So since this one is already low, so you're going to negate it so that it becomes high. So this one would have a small node next to it, so it means you're negating it. You would also negate Q2, as you can see. So if you negate Q2, so at this state, if it is 0, it becomes 1. In a way, you want to get all the states 1, and then this is going to produce a 1 at the output. So you would negate this one, and you would negate the next one as well. So this one is corresponding to Q2. This one is already high, so you would not negate it. Yep, this one is corresponding to low, so you would negate it. And this one is high, so you will not negate it. So when you reach the state there, when you get 1 0 1 0, so if you feed that to an AND gate, it's only for this particular state that this output here would be high. And what can you do with this now? You can connect it to all your clear lines this way. So I'm just showing one line there. So you're connecting all of this to your clear. Oops, so this is your clear line. This is now going to do your modulo 10 up counter. If you don't put that additional logical circuit there, it's going to count from 0 to 15 and then go back to 0. So what are you doing here? When you reach 10, which is 1 0 1 0, you are now using this state at your output to actually create a signal, which only this combination here 1 0 1 0 would create a high here, and then you use this one to actually clear all your Theta flip-flop. So in a way, you're forcing your counter when it's reached 9 not to go to 10 now, because at 10 it just clears all the different flip-flops, and then you start back at 0, and then it's going to count 0 to 1 2. So this is what you see in the notes here, this one here. So this is what you can see, that arrow there showing that when you reach that state there, it actually resets everything back here and then keeps counting. So I hope you are able now to understand how to do the modulo counter, which is not 2 power n minus 1, not 2 power n rather,